Maryna Nesterenko, please. Constructions of representations and realizations of Lie algebras. Please, Maryna.
Thank you for your kind introduction, and I would like to thank the organizers for their nice job, for the possibility to present my talk here. Today I would like to tell you something about how we can contract realizations or representations of Lie algebras. Why it's important? It's important because this allows us to connect different models of mathematical physics or whatever, of any system, which connected to partial differential equations, which have some good Lie algebras with symmetries. If we know how we can connect Lie algebras by limiting process, by sending some contraction parameter, say to infinity or to 0, then we can connect respective differential equations. To do this, first of all, we need to connect differential invariants. And to connect differential invariants, we need to connect realizations. And now I would like to tell you how it can be done, because this problem is not so obvious and it needs some elaboration. Well, let me start from definitions. Let me have some vector space V. It's an n-dimensional vector space over some field. Now, field is not fixed yet. And we consider the set of all possible Lie brackets on this vector field. So, in fact, Rn is an algebraic subset of such a variety of linear maps. So, we identify a fixed Lie algebra with a product in this set of possible Lie brackets. So, Lie algebra J is our vector space V with a product of it, mu, or me, how to pronounce, I don't know how to pronounce it correctly. On this space of Lie algebras, of n-dimensional Lie algebras, acts the general linear group. And this general linear groups acts in the following way. It acts as it's written in this equation. So, we can denote the GLV orbit of fixed product, of fixed rule of multiplication by O of me. And then we can consider a closure of this orbit with respect to the risky topology. That's precisely the things what were described by Professor Pelikaros two lectures before, just 2 lectures before on this conference. And now we can define the contraction of Lie algebra. We will say that J0, Lie algebra J0, is a contraction of the Lie algebra J if mu0 belongs to the orbit closure with respect to the risky topology of mu. Usually such type of contraction, when we use the risky topology and when we use arbitrary vector field, is in literature called degeneration. And what is called contraction will be given by next definitions. The previous definition is very general. It allows us to prove some necessary contraction conditions. It allows us to describe the relations between different algebras, not only Lie algebras, as you have seen in previous 2 lectures before. It allows us to connect different algebras with different structures. But to work for physics, to work for the theory of differential equations, we need something more explicit. Usually we work with a field of real numbers or with a field of complex numbers. And in this case, we can define these limiting processes without the risky topology. We can use standard Euclidean topology. In this case, we can consider such a transformation, which we usually call contraction matrix. It's a transformation that sends semi-open interval 0, 1 and send it to the some transformation from general linear group over our vector space, and parameterize product our mu in the following way by these transformations. Then for any value of parameter epsilon from this semi-open interval, we get the isomorphic representative. We get the isomorphic Lie algebra. But when we take the limit, we can come to non-isomorphic case. That's how we construct this path that moves our Lie algebra through some path of isomorphic Lie algebra to non-isomorphic one. And this result with such a product, with such a Lie bracket, we call the contraction. If we fix a basis in the space big V in our vector space, then Lie algebra is uniquely defined by structure constants in this basis, uniquely up to automorphisms, of course. Then we can redefine notion of a contraction in terms of structure constants. If you look at this equation 1, you see how we can define contraction in terms of structure constants. The theory of contractions is very interesting. One of the most famous examples of contractions is the relation between relativistic and classical physics. When we send velocity of light to infinity, we get a model of classical physics. The same can be done for different theories, for different Lie algebras. But let us understand what we mean by realization to understand how it can be done for differential equations. Okay, let us define Aug the group of automorphisms of our Lie algebra and consider inside of it internal inner automorphisms. Then we will take some open domain in Euclidean space R to M, we denoted by M, big M, and we consider vector fields, smooth vector fields. I mean vector fields with good coefficients. It depends on the field. The real complex numbers we can consider smooth or anyway, we consider infinitely differential functions on this manifold. So vector M is vector fields on this manifold. Then realization of Lie algebra in vector fields on M is a homomorphism that sends our Lie algebra to this vector space, space of vector fields. If the kernel of this realization 0, then the realization is faithful and it's unfaithful otherwise. If we consider local coordinates on this manifold, then and we fix basis, of course, of our Lie algebra, then we can represent the realization as a realization of each fixed basis element. In this case, it will look like first order differential operator with good coefficients. These coefficients are good. Smooth or whatever, what we need for our problem. There I use shortcut for DL is just D is partial derivative with respect to the XL. And these coefficients should be good functions. Well, now let us consider some theory about realizations that we need to know, to explain how we can construct this algorithm of contraction of realization. Okay, if we fix some point from our manifold, and we will consider our realization at this point, at this fixed point, then we can form matrix. It will be matrix of some real or complex numbers. It depends on the field. And we will study rank of this matrix. The rank of this matrix will be called rank of realization at this point. And it's obvious that the rank of realization cannot exceed the dimension of Lie algebra, because the dimension of Lie algebra is number of rows, and the number of columns is exactly the dimension of our manifold on which we construct this realization. So we know the dimensions of these matrices, and in accordance with these dimensions, we can construct differential. First, at the beginning, we don't construct differential invariants. At the beginning, we construct just usual invariants to eliminate all inessential variables from realization. So if the dimension of the matrix more than n, we can take off all the rest of variables just by replacing them by invariants. Well, now we can construct realizations of Lie algebras in several ways. The first way is direct method. What should we do? We should take this first order differential operators in general form with arbitrary functions coefficients and to substitute them into the commutation relations of Lie algebras. We get system, a rather complicated system of partial differential equations. After we solve this system, we get realization. There's another way to solve this problem is so-called algebraic approach, when we can construct differential one forms that correspond to our Lie algebra, and then to recover left invariant vector fields from these differential one forms. The advantage is that construction of differential one forms can be done without solution of differential equation. In fact, the solution of differential equation is hidden inside this theory because you see we construct differential one forms in such a way where we have exponentiations of the joint actions everywhere. In fact, this exponentiations is solution, but we can solve this equation differential in general form, and we don't need to solve all this system of complicated partial differential equations. Well, if we do it in the following way, then we can use the fact that left invariant vector fields and differential one forms are dual to each other. So just inverting the obtained matrices of differential one forms, we can get realization. Of course, we need to find the joint action to each basis element. Of course, we need to exponentiate these matrices. Of course, we need to look for inverse matrix. It's not very simple problems, but these problems are more algebraic. These problems from the theory of algebra, but not from the theory of differential equations, and then can be more or less successfully automatized. And why I am talking about this method? Because this method is precisely the key idea of our algorithm, how we can, that allows us to construct contraction of realization. Well, let me tell you a few words about transitive realization. Of course, in this way, we can construct a transitive realization. A realization that not just transitive, but the realizations of the Lie algebras, the respectively group of which act not only transitively, but primitively. I mean that there is no isotropy subgroups. The realization that corresponds to the transitive action, to the primitive action of the respectively group, we will call the generic, because all the rest of realizations can be constructed by projections. Here you see how if we have some subalgebra and we ordered a basis before application of the previous construction in such a way that subalgebra is formed by the last, say, k basis elements, then we just can cut this tail of our realization and get realization that corresponds to the transitive action with respect to some isotropy subgroup. That's just construction. So this method works not only for transitive and primitive action realizations, but to all positive cases, to all transitive cases, and moreover, this method can be generalized to non-transitive action as well. It can be done. Well, so now go back to contraction and to understand what we can do with realization. Well, on this picture, you see the general picture of contraction, all possible contractions of three-dimensional Lie algebras. The three-dimensional Lie algebras, all possible real field. Now is the field of real numbers. And in this case, you see the general picture. If you take three cases, take three-dimensional abelian Lie algebra, if you take Heisenberg algebra, and one more algebra, which in classification, according to Bogdanov's classification, it calls A3.2. The commutation relations are written here, you see. 3.1 is Heisenberg, and 3.2 is this one. This one, Lie algebra. We know that there is contraction between the Lie algebras. And this contraction can be made by the following matrices from 3.2 to Heisenberg by the diagonal matrix with the elements epsilon and epsilon here. During the contraction, we send epsilon to zero. And 3.2 to the abelian one and 3.1 to the abelian one by this one. Let me note that this matrix of such a form is appropriate for any contraction to abelian from any Lie algebra fixed dimension to abelian one. And if we apply the corresponding linear transformations to our realizations and then send parameter 0 to 0, we will get good realizations of this algebra. So you see this case 0, D2, 0. Okay, and the second case is 0, 0, 0, 0, 0, 0. Yes, the result does realize this contraction, but we got unfaithful realizations. What very bad for application. We can't construct invariants, differential invariants, or invariant equations, or connect theories after that. And this picture is expected. It was already predicted in work by Inonio and Wigner. Upstairs at the beginning of this page, you can see a part of the paper from 1953 where they predict the situations that it will happen. They were considering it not in case of realization, but in case of representation, but the story is the same. And here you see several papers by the people who try to overcome this problem. How it usually done? In the case of representations, we usually, not we and they, everybody, usually use similarity transformations that depend on parameter and apply it before apply contraction, just to keep something, not to make all the metrics 0. And in these two works by Ivanova-Popovich-Sofoklius, Vaneva-Popovich-Sofoklius, they were moved from realizations to respective group action and use special parameter-dependent additional transformations in the case of groups, Lie groups. So all the ways to introduce contraction into realization or to representation were very tricky. Each time you should invent some trick for concrete fixed example. So what we propose to do, what method we proposed here? First of all, let me mention that we can, in general case, introduce parameter-dependent equivalence transformation in two ways. The first transformation can be introduced as automorphism of our Lie algebra that preserves structure constants, but can introduce parameters. The second way how we can introduce parameter to our contraction is to consider diffeomorphism, parameter-dependent diffeomorphism of manifold M. But in both these ways, we again should to discover some tricks to do this. But what we can do using the method by method of construction of realization. First of all, we can get parameter-dependent structure constants. So we can take contraction matrices that are known, apply them to structure constants of the initial Lie algebra, and get parameterized structure constants. That will be structure constants of the isomorphic representative of the same Lie algebra. Then we look for a joint representation, and this joint representations will depend on parameter. Then we should exponentiate them, construct differential one form, construct inverse transformation, and we will get realizations that are already parameterized. For example, consider the same cases, 3A1, abelian three-dimensional, 3.1, and 3.2. For these cases, if we apply this procedure of construction of realizations for parameterized structure constants, we will get realizations in the following way. You can see that for value parameter equal to 1, we will get the realization of the initial Lie algebra. And when the parameter epsilon goes to 0, we will get very good, faithful realization of the contracted Lie algebra. The same works for abelian. You can see that we again get faithful realization, and we avoid this necessity to construct some tricky transformations. So for realization, a method works, and we checked it on many examples. It works very well. Let me show you some ideas. So that's a general algorithm, how it can be done. Of course, if we need to find limiting process for a fixed equation, then the appearance of realizations that corresponds to differential equations, invariants, and so on, to the fixed equation can be not in canonical form, not in that form that gives our method. Then we need to relate them. The biggest problem how to relate them is to understand to which realization it corresponds. But here we have some very nice trick. It's not written here, but I can tell you how to. No, it's written here. We should define the subalgebra that corresponds to realization. To define the subalgebra, we should consider our realization in the points where it's tangent space to our group. This point, usually this point 0, it depends, but usually it's 0. So at this point, at this tangent point, we should consider values of our realization and take kernel, and kernel will correspond to a subalgebra. And each realization is inequivalent to realizations equivalent if they have some same subalgebra, and inequivalent if they have different subalgebras. In this, I mean isotropy subalgebras, isotropy subgroups of the corresponding Lie groups. Well, so in this way we can define the correct representative, parameterize it, construct, and so on. But the disadvantage, if we need the concrete form of realization or concrete form of differential equations, then we need to look for differential equations that will relate them. We know that they exist, but we need to spend time to solve these systems of differential equations, of partial differential equations, to find transformations that will relate one to another. That's how it works for realizations. Let me say a few words about. Let me say.
Maryna, 2 minutes.
Okay, I will finish very quickly. I will say too much about representations. Let me show you the easiest way. You know, if we have realizations with linear coefficients, if the basis operators is in such a form, then the matrices formed by these coefficients of these linear combinations commute precisely in the same way as our basis elements. So if we have representation, instead of it, we can consider linear realization with linear coefficients and do everything the same. The only problem, the case when representations have higher dimensions than dimension of Lie algebra. It's happened very often. For example, if you consider the simplest case, SL2 case, it has representations in many dimensions, but dimension of algebra is actually 3 only. So this method will work only for those that dimensions is equal to the dimension of Lie algebra or less, because otherwise we wouldn't be able to propose this case, and our metrics will be. But we have some ideas how it will work, but only for simply algebras. We use Cartan subalgebras and construction for presentation and introduce this contraction parameter at that stage. But for solvable, we have no idea how it can be done. Of course, they will be got by contractions, but if you look at this picture, I'm finishing at this picture, not all solvable can be get by contractions, because we have solvable at this stage and all the realizations are there. But these pieces are still will not be constructed. So with these cases, if the dimension of representation higher of the dimension than the dimension of the algebras, we have no ideas what to do. That's all. I'm sorry that I use so much time. Thank you for your attention.